Thank you. It's a great pleasure to be back here in Boulder and get to spend a few days sharing with you something I love, namely cosmology. So let me first tell you just a little bit about myself. I am from Sweden. I don't know if you can see it, but this is where I was born and raised in here. And the good news is these lectures will not be in Swedish. Now that I've told you a bit about myself, let me ask you a little bit about you. So, who is a graduate student? Raise your hands. Who is not a graduate student, but a wolf in sheep's clothes? 1, 2. All right, good. Who was born in the United States? Who was born outside of the United States? Who was born in Europe? In Asia? Awesome. In Oceania, so Australia, New Zealand? Nobody. What about Africa? Who's born in Africa? Yay! Where? Egypt. Salam alaikum. And what about South America? ¿De dónde eres? Ah, qué bueno. And what about elsewhere in North America? Like, do we have any Canadians? Eh? Yeah. And what did I forget anywhere? Good. So we have quite a nice diverse group. That's awesome. We're going to talk about our universe. So it's the first approximation. All the continents are in the same place on these scales. What about subject-wise? I'm curious, who has as their main focus particle theory? Who has as their main focus particle experiment? Or phenomenology, let's say. Oh, there are a few more hands. Good. Who has as their main focus something else? For example, what would you say? Gravity, relativity, and you? And what? Supersymmetry breaking? Very good. So we have a nice breadth of fields as well. That is awesome. So let me tell you about the cosmic plan for these lectures. You've had these nice lectures about dark matter already, but this is the only set of lectures about cosmology as a whole. So first of all, there are a lot of basic questions in cosmology we don't know the answer to. It's not a dead field, like calculus, which was all figured out 100 years ago. We know that 95% of our universe is dark matter and dark energy, but what exactly is that stuff? We would really love to know. Where did everything ultimately come from? What is the deal with our Big Bang? What are the ideas there? And what's going to happen in the future? A lot of very cool questions we're going to be hitting on big time. That connects with even bigger questions also, like how big is ultimately our physical reality. I'm not going to be talking about these really wild things in these 3 lectures here, but if you're into that kind of stuff, the organizers have asked me to give a public lecture about that tomorrow night, where you're all welcome to come and hear more about parallel universes and other wild stuff, which ultimately comes much largely from cosmology. And if you can't come tomorrow night and you have questions about this stuff, these wilder things, you're welcome to go to my Facebook page and email me and send me questions there. I love those questions as well. In terms of our game plan for these 3 lectures, we'll be talking a lot about theory. We'll be talking a lot about observations. On the theory side, I'm going to teach this the way I like to think about it, the way I feel is the most natural framework, which is by organizing things in perturbation theory. I'm going to show you that by just the 0th order, there's so much stuff we can do, ignoring all the fluctuations in our universe. And I'll explain what I mean by that. And then, 1st order, add clustering and clumping in the universe and study how this grows into all these interesting things like galaxies and people. And then higher order things. Finally, on the observational side, this is a very, very rich field. Cosmology used to be considered a very flaky field, somewhere on the borderline between philosophy and metaphysics. You know, you could speculate with your friends over some beer about how old our universe was, and then you could go home because there was little else to do. Now we have all this data, right, in many, many different areas, and I'll be mentioning in particular a bit about supernovae, galaxy redshift surveys, cosmic microwave background, and an emerging technique, 21 centimeter tomography, which has the potential to be the most powerful of all. And the game plan here involves two components. On one hand, I really want you to get the basic foundations really, really well. So we're going to be doing that with math on the blackboard, which I feel is the best way to just really make sure you really understand the math. But I also want to make sure that since most of you are not working in cosmology active as your main focus, that you get a broad overview of all the different ways in which cosmology can be useful for you in your research. And if I were going to do that all on the blackboard, we would be spending a one semester course here, which we don't have. So I want to, in addition to complement the math on the board, give you a brief panorama of exciting things that are going on with PowerPoint slides, okay? So that you know later on in your research if there's something cool related to what you're doing, you're like, wait a minute, I think I heard about that in one of Max's lectures, and you know where to go look it up and read more about it, okay? So that's the basic plan. The last thing you need to know is I love being interrupted with questions. So we have a lot of time together. Yes, we have a dedicated question session, I think tomorrow afternoon as well, but if there's anything that's unclear to you when I'm going through things here, or there seems to be a missing minus sign or whatever, you're almost certainly not the only one in the audience wondering about that. So if you just shout out, a lot of other people will be happy too. And I love being interrupted, so ask questions whenever, okay? So without further ado, let's delve into cosmology. So what have we learned, first of all, during our about 100,000 years as humans on this planet about our place in space? Let's just very, very briefly remind ourselves of that. And to do that, let me just I'm hoping you're going to stay awake despite this, since it's kind of early in the morning. Let's just very briefly remind ourselves by zooming out a little bit from our planet. It's pretty remarkable, I think, really, how our perspectives have changed. 2,000 years ago, when people first figured out the size of our planet, thanks to Eratosthenes, they were like, whoa, it's so big. And now we feel that this is just very, very tiny, of course. So the meter was, of course, defined so that it's 10,000 meters to go a quarter of the way around. Here you see all the artificial satellites that we humans have put up as these green lines here. And it took a long time to get any sort of accurate distance measurements for things outside of our planet. The ancient Greeks cleverly figured out the distance to the moon and got it almost exactly right. Aristarchus did that, but they got the distance to the sun wrong by a factor of 10 or so. So for 1,500 years, we thought the solar system was about 10, 15 times smaller than it actually is. Here you see the radius of the moon's orbit. You all know that it takes about 8 minutes for light to reach Earth from the sun. So Copernicus thought also that, so even though he had the basic order of the planets right and the motions right, he thought everything was about 10 times, 15 times smaller. For the outer planets in our solar system, it takes hours for light to get to us. And yet, that's of course nothing compared to the stars. If you see some nice stars tonight, you're looking at things that typically happened a few hundred years ago. So someone out there wouldn't see Taizé summer school here, but they might see the American Revolution or something like that. When my grandma went on her first date ever, this was our universe. They didn't know that there were other galaxies. There were just a bunch of stars. Only in 1925 did Edwin Hubble realize that we live in this much grander object. We're part of something much bigger, this galaxy with hundreds of billions of stars, 100,000 light years across, our Milky Way galaxy. And now we know, of course, that our galaxy is just one among a vast number of galaxies that you can see here in beautiful different colors. And these, in turn, are part of grander structures, groups, clusters, superclusters, and gigantic filaments. This is the data from the Sloan Digital Sky Survey project I've had a lot of fun working on over the years. And yet, there's still more that we've mapped out there. You see, beyond all this, with the galaxies, you see this very bizarre blue and yellow sort of sphere, this ball. Oh, what on earth is that stuff? This is the cosmic microwave background radiation. And I want to make sure that by the end of today's lecture, you all feel really comfortable about understanding exactly what this is and what it can do for us. Let's get some light on this subject again before you guys get too cozy here in the dark. To understand, so for much of this, we just went farther and farther out and saw more and more stuff. That's pretty intuitive. But to understand the cosmic microwave background radiation and so on, we also have to understand not just our place in space, but our place in time. Okay? Fortunately, that's very easy in cosmology because, as you know, the sky is basically a time machine. Right? If I look at you here, for example, what's your name? Nicholas. I see Nicholas. I see you the way you looked about 6 nanoseconds ago, because that's how long it takes light to reach me from you. And we see the sun 8 minutes ago. This is the Hubble Ultra Deep Field, which is a photograph taken with a 3-month exposure from a camera that's 2.5 meters in aperture, has a 2.5 meter aperture from the Hubble Space Telescope. And we see things here that are so far away that the stuff we see happened up to 13 billion years ago. It's pretty wild. And the whole image here is zoomed out so much that it would cover only the head of a needle if held at arm's length. So by looking at different distances in the sky, we can see, of course, what happened at different times in the past, far, far away. And then, because of a very powerful idea, which is that when you look at this, you see it looks kind of very similar everywhere, really. One of the key things we've learned about poking around in space is, statistically, there's just a bunch of galaxies here, a bunch of galaxies there. It seems like more or less the same stuff has been happening independently in many, many different places. That means that if we can learn what happened really, really far away over there, that's probably very similar to what happened that long ago over here. We also learn about our past simply by looking out into the sky. So I think it's very ironic that it's easier to learn about what happened 13 billion years ago than it is to find out in great detail what happened 20,000 years ago, or sometimes even 20 years ago, if you look at great controversies in history and who really murdered that person and where is Jimmy Hoffa buried and so on, right? In astronomy, want to know about the past? We just look. Okay. So what have we learned so far by looking at different distances in the past? Because of the relatively low luminosity of the projector, I'm going to torture you by flipping off the switch a few times when there isn't something I really wanted to see here. So apologies for that in advance. We've learned, first of all, that about 13.8 billion years ago, something really weird happened. Okay? We don't know exactly what it was, but we call it our Big Bang. I'll be talking more about it. However, we have a great deal of knowledge of what happened since then, during the subsequent 13.8 billion years. There were basically 2 physical processes that happened. The first one is expansion. Okay? Stuff expanded. All the gas that filled our universe, therefore, gradually got diluted from denser to more rarefied. And then, of course, when you expand the gas, it goes from being hotter to being cooler. That's how your refrigerators and air conditioners work. Okay? And when I talked in the beginning about how I'm going to organize these lectures by perturbation theory, when I talk about 0th order perturbation theory, I mean this, the expansion process. We can ignore completely any clumping and just make the approximation that the density is independent of position. Temperature is independent. Everything is independent of position. And it's just changing over time. Okay? So we're going to spend much of today talking about, and probably all of today, about this first process and everything that comes with it. Yeah? Why did I cross out some numbers? Oh, because we've measured them more accurately since the slide was first made. I'll explain why things have gotten so much more precise. Okay? The second process is a transition from smooth and boring to clumpy and interesting. Okay? So now we're doing first-order perturbation. We're going to do first-order perturbation theory. We'll look at, early on, the universe that we inhabit was full of gas, hydrogen mostly, much like the air in this room. Okay? And raise your hand if you can hear me. Why can you hear me? Sound waves, exactly. So this room is the pretty good approximation of uniform density air. But there are perturbations. The density varies from point to point. If I speak about this loud and you measure the density about this far from my mouth, the variations are about 10 to the minus 5, a thousandth of a percent, which coincidentally is almost exactly what it was in our early universe. Okay? So we had these sound waves propagating through the hydrogen plasma, or hydrogen gas that was back then. And then gradually, gravity amplified these fluctuations. In this room, sound waves are very stable. They don't get amplified and get bigger and bigger, and then you form a black hole here, right? But in our early, what we're going to see is on very large scales, there's an instability. If you have a sound wave whose wavelength is longer than a certain critical wavelength called the Jeans wavelength, it actually grows in amplitude over time. So gravity actually amplifies these tiny fluctuations early on into the large-scale structure, the galaxies, the planets, and all the great stuff that we have around us today, transforming our universe from this boring hot gas to this interesting cosmos that we flew around in a few moments ago. Okay? And we're going to see that with first-order perturbation theory, we can study that very successfully. Now, before we turn to the blackboard and do math, I wanted to summarize in more visual form again the key parts of this history of our universe that I've talked about, so you're motivated to sort of suffer through the math. Okay? So let's do that. So very early on, we had all this stuff which was expanding very fast, flying apart. That's the 0th order thing. But you see, it's also getting gradually clumpier and clumpier as gravity is clumping stuff together. And to let you see that a little bit more clearly, what I would like to do is show this again in removing the expansion, just having coordinates that expand with the stuff. Because now you can see very clearly how gravity is able to just take something very uniform and make it clumpier. And even before we do the math of this, it's actually quite easy physically to see why gravity does destabilize things and clump things like this. It's because if you have things that are completely uniform, translationally invariant, they have to stay that way by symmetry, right? The law of gravity doesn't pick out any special place that can be a nucleus of clumping. But if you have a little bit more stuff here, a little bit higher density here than in the surroundings, the gravity from this overdensity will attract in more matter from its surroundings. And this little clump gets bigger, which now gets better at stealing stuff from the surroundings and draws in still more stuff and still more stuff. And you have a runaway instability. That's what happened. That's why our galaxy formed in the first place. So it's 10 to the minus 5 fluctuations, then they grow to 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1. And by the time they get to order unity, all sorts of nonlinear processes start happening very, very rapidly, and boom, here we are. One can zoom in to one of those overdense clumps. This is a supercomputer simulation from Matthias Steinmetz and his group in Potsdam, Germany, for example, where you look on the left side at a side view of the same region of space you see from a top view on the right. And he's put into his supercomputer not only the laws of gravity, general relativity, but also some simple laws of gas physics. And you see eventually gas gets so hot in certain places the stars form. And you see a lot of stars. It's pretty chaotic. The formation of our Milky Way was not very abrupt. It was more like an ongoing series of traffic accidents on the highway, where whenever you had forever more clumps just crashing into this stuff. And even today, if we look around in space, we see our Milky Way galaxy is actually busy gobbling up a little innocent neighbor galaxy, Sagittarius dwarf. I don't know how innocent it is, but this is what's happening. And what you can see now after a while in this simulation is actually that it's beginning to look a little bit like a spiral galaxy. It's kind of flat from the side and kind of round from the top. What's also seen here is that where the dark matter is, which we can't see with our eyes, but that's super exciting for you guys because we can make these predictions for how the dark matter should be distributed, and then we can predict how many dark matter particles per second should pass through Earth, and the laboratories here where we search for it, right, in direct detection experiments, making a very direct detection with dark matter, which you heard these nice lectures about earlier. Yep.
So a lot of these simulations start around the projections of 2025. What does that correspond to when
What that corresponds to in time?
what about these?
That's a very good question. Let me show you. Let me just cut ahead a little bit to a slide which answers exactly your question. So here, I'm going to come back and explain what this is. But this is the region of space from which light has had time to reach us during the 13.8 billion years since our Big Bang, okay? All to scale. We're here at the center, and this is the most distant parts of this. And you mentioned redshifts, 1, 2, 3, 4, 5. We'll come back and talk a lot about what that is. But on the same scale, if I put in what you asked about, namely when were these things, this is what it looks like. So basically, stuff that happened 13.8 billion years ago comes from the most distant regions you can see. Stuff which comes from about half the distance happened 12 billion years ago. So this is quite a non-linear mapping. Okay? So most of the volume that we can actually see comes from stuff which happened very, very close to the beginning, actually. And I'm going to derive for you the equations of this, so this will be a little more clear. But in other words, the simulations you looked at there start typically, back here or so, or at times corresponding to light that was given off, back then, and then back to the present. So, and that's how far back you have to look with a telescope to see those sort of early stages of cosmic evolution.
Can I ask one?
Of course, I love questions.
So back to this slide, when you showed the inflation CMB, shouldn't there be like a question mark at some point, like between inflation and CMB? Should that be, you don't really know?
There totally should. Now, if you do that question mark to scale, it'd be way too small to see with the eye. Because, as I'm going to tell you, we have a very good understanding, actually, of what happened after the first second or so. And right now, we're at about 10 to the 17 seconds. So in terms of if you plot it like that, in terms of actually distances, it's an extremely thin layer where we don't know what happened. So it wouldn't fit there. But if you instead plotted, say, as a function of energy or redshift, or then it's a huge range. So I would say basically we have a very good idea what happened back to 400,000 years after our Big Bang, because we can see all that because space is transparent. Then we have a lot of good ideas of what happened between the first second and then. Basically because even though we can't see it, we can find sort of fossil evidence from what happened then. We haven't seen the dinosaurs, but we found all these bones, and if you see a Tyrannosaurus rex femur, it's pretty convincing, unless you're some kind of creationist from Kentucky, whatever. And we flew over yesterday. And we have exactly the same thing in cosmology, because basically, as I mentioned, our universe has been expanding and cooling off, right? And all this hydrogen that fills space was just hotter and hotter and hotter the farther back you go. If you go back to the first second, you calculate that hydrogen was about as hot as the hydrogen is in the core of the sun. And that we know exactly what hydrogen does at those temperatures. That's still very low energy compared to what you're studying in your research mostly. Standard nuclear physics. It does fusion. Hydrogen fuses into helium. We see it happening in the sun. We can measure the neutrinos the sun produces from the fusion reactions. So our whole universe should have been a giant fusion reactor during the first few minutes, in fact. And you can calculate how much fusion products would have been produced before it got so cold that the fusion reactor switched off. and you calculate that you would produce about 25% helium and a little bit of other stuff. Then we go out and look how much helium is there in the distant universe, and we measure 25%. Pretty impressive. It's just as cool as finding a Tyrannosaurus rex femur. And you also predict a little bit of how much helium-3 there should be, how much deuterium there should be, and how much lithium there should be, and very good evidence. So we're pretty confident back to 1 second. After that is where the question marks get bigger, and we don't really know exactly even how baryogenesis happened. And then we just have a lot of cool ideas. If there's time, I'll talk a bit about inflation and the hints we have that we know what we're doing, even back to 10 to the minus 30. 10 to the minus 34 seconds. But right now, the boundary of our knowledge, the frontier of our knowledge, goes at about 1 second. And then after that, it gets more speculative. So that's a very good question. Coming back to just wrap up very briefly the story of how our history of our universe before we go all mathematical. Zooming into still smaller scale here of the scale of our solar system. When you have a gas cloud, it contracts under gravity, but it can't just collapse to a point because of angular momentum conservation. So it tends to collapse into a pancake and then gradually get denser and denser until the central density of this gas pancake gets so hot that nuclear fusion ensues there, like we just talked about, and a star is born. In the meantime, it also clumps into planets in the outer parts of this disk, and then the nascent star eventually just blows away with the radiation pressure, this disk that it formed out of, and it reveals these planets. And since all the angular momentum came from the angular momentum of the cloud, it's no surprise that all the planets in our solar system are orbiting around the sun in the same sense, which is also the same sense in which the sun is itself rotating. So this is the basic story now of how our solar system got here. And if we zoom into still smaller scales, we come to Earth. You know, I used to think that plate tectonics was a very slow process, but actually the 200 million years you see here is a very short time in the cosmic perspective, where I was just talking about 13.8 billion, right? So our planet is very dynamic. And just for fun, let's zoom in even a little bit closer still and take a look at what's happened on our planet more recently, courtesy of some of our friends from Springfield here. The cosmos has kept impacting life on Earth continuously, even after Earth was formed, even quite directly, like the impact 60 million years ago of this giant asteroid that smacked down off the Yucatan Peninsula in Mexico. And that was very good for us, because we mammals were just these little guys running around trying not to get stepped on, right? And this was our lucky break. All right, so that was a brief story of how the Tazy Summer School got started. And hopefully now I've motivated you to suffer through a little bit of math to see how we can get more quantitative about this. So let's get talk about a bit of how to do this math. So raise your hand if you've studied general relativity. Awesome. Raise your hand if you have not studied general relativity. Okay. Don't worry. What I'll be doing here is going to be very self-contained. Is it actually possible to read this in this dim light? Raise your hand if it's invisible. Yeah, a lot of hands. Is there any maybe we could borrow a projector from somewhere else for not for today, but for like tomorrow, because I think it's just an old bulb. Okay, wonderful. So this is the Friedman-Robertson-Walker metric. We're going to look at the zeroth order at the approximation that things are exactly the same everywhere in space. So there's no spatial position dependence of everything, right? And the first order, we add these perturbations on top of this, and look at how they evolve. And the really most lucky and useful thing in cosmology is the simple fact that 10 to the minus 5 is much less than 1. That sounds like the dumbest observation you've heard during the entire summer school, but it's super awesome because 10 to the minus 5 is much less than 1. That means that you can linearize everything. You take these complicated coupled partial differential equations, which are the Einstein field equations and the Boltzmann equation of fluid dynamics, all this. You linearize everything, and then you throw away all the second order and higher terms, and you know that what you just threw away is accurate to 5 decimal places. I mean, how awesome is that? So it's very, very accurate linear perturbation theory. And once you've linearized everything, there's another wonderful thing you can do. Since you have spatial homogeneity and linear partial differential equations, you can Fourier transform this now. And then all your different Fourier modes decouple. That's what always happens if you have something which doesn't depend on position, right? You Fourier transform it. You just have all these derivatives, and then you just get algebraic things. This is the key reason why theory has been so effective in the cosmic microwave background, for example, because by working linearized in a sort of Fourier space, or a spherical harmonic sometimes, you can basically track one Fourier mode at a time to see how it grows over the 13.8 billion years. Very fast. You can download the CMB fast software online, and it'll do your whole universe for you in 1 second or something. It's really, really great. It's only when you go to higher order that things get more complicated. But let's now get a little bit more down and dirty with the zeroth order. So let's get some more light on the subject. Let's see if we can find a very thick piece of chalk. Awesome. So yellow is my favorite color. So let's just begin again by just writing down the metric, the Friedman-Robertson-Walker metric, which describes the most general space-time where things don't depend on where you are, which we call in geek speak, homogeneous and isotropic. So the most common way of writing it is like this. So we're using polar coordinates for the positional part. And when you just stare at this, you see, well, what is there about this that contains any information? Well, the t here and the r and the theta, they're just the coordinates, of course. But there is this function, a of t, which is an arbitrary function to be determined. And where we're going to see that we can think about this is the size of our universe as a function of time. If you pick any two galaxies, they will eventually go farther and farther apart if they're distant. How does that function, what is this function of time? Most of the quest when we study our universe to zeroth order is to just measure this function, figure out what is it. So first we're going to just work out the equation that this function is supposed to solve. Then I'm going to be telling you about how using different kinds of tools like supernovae and other things, we can actually measure this curve. And I'll often talk about the cosmic expansion history as the synonym for this function, telling us how fast has our universe been expanding at different times in the past, okay? What else do we have here? There's this k. K is just a constant, which can be either -1 or 0 or 1. If it's 0, then we have a flat space because we recognize this is just normal So if things are flat, then the whole Friedmann-Robertson-Walker metric just becomes dt squared minus a of t squared, and then I can just switch out from polar coordinates to Cartesian coordinates if I want, and just write this in the very familiar way, dx squared plus dy squared plus dz squared. Fortunately for you, observationally, our universe is indistinguishable from flat, actually. So the math is actually easier than most of us thought when we're grad students, where the more complicated versions where k is different need to be used. So let's understand a little better how to think about this metric, okay? Because that's one of the most central things in cosmology. So let me just draw a little space-time diagram, t and x, and then let's look at 4 different events. Suppose I have event A. It's when the first Taizé summer school is held in this galaxy over here, okay? And let's look at event B, maybe, when the second Taizé summer school is held in that same galaxy. They're at the same x, right? X is one of my 3 Cartesian coordinates here. And then let's look at another galaxy where there's a summer school called the Shmazy summer school, and the first one is held here, and then there's a second Shmazy summer school held there at some later time, t, okay? And let's try to understand a bit about how do we think about this space-time in terms of these quantities k and in particular a in this Friedmann-Robertson-Walker metric. So first of all, I've picked these galaxies so that they are staying at a fixed x. So these coordinates that you see in here, we call them co-moving coordinates. The x and the y and z, or equivalently in polar coordinates, the r, theta, and phi, we call them co-moving coordinates. And we'll see momentarily why we do that. How long time, first of all, did it take, according to the people who lived on this first galaxy, between the first Taizé summer school and the second summer school? Do you know how long it was between the first? Was it annual, 1 year from the first to the second? But this is general relativity, so we need to be very rigorous about durations because it's observer dependent, right? So according to an observer who stayed on this galaxy, the whole time, how long did it take? Well, delta t, the time that elapsed between event A and B is, of course, just the integral of d tau, integrating through space-time from A to B, right? So we're going to integrate like this. We're doing it at fixed coordinates here. So none of this, so dr, d theta, and d phi are all 0. So the only part that's going to enter is going to be this part. So this is just going to be the integral of the square root of the dt squared. So it's just the integral of dt. So it's just delta t, which is just the t coordinate at event B minus the t coordinate of event A. Okay? So this tells us our first very useful thing about how to think about the Friedmann-Robertson-Walker metric, which is if you are a so-called co-moving observer, if you're just hanging out at fixed co-moving coordinates, then the time that you will measure on your clock is just this this t coordinate in the Friedmann-Robertson metric. So in other words, this implies that the t coordinate t measures time observed, or proper time observed by co-moving observers. And we are, to a reasonable approximation, co-moving observers. Okay, Earth is moving around the sun, and we have a little bit of a random velocity, but on the cosmic scheme, our galaxy is pretty much just hanging out at a fixed co-moving coordinate. Certainly, if we so this is not such a shabby approximation, the time that we actually just measure. Okay? With some corrections we'll come to in perturbation theory. What about distance? How far are we from the Schmazy summer school? What is this distance here? Let's take a look at that distance d. Well, the distance from A to C, how far is that? Well, we do an integral from A to C now through the metric. This is now no longer a time-like separation, but a space-like separation, right? So we're going to take minus d tau, square root, and we're going to integrate that, right? And what do we need to keep track of now in our square root? Well, now dt is equal to 0 because we're doing it at a fixed time coordinate, right? And let's do it in the Cartesian coordinates I drew. Suppose we're just going in off the other galaxy. The Schmazy summer school is just offset in the x direction. So dt doesn't enter. dy is 0. dz is 0. We just have a squared dx squared. Square root of a of t squared dx squared equals integral of, so we can take a out of the integral altogether because it doesn't depend on x. This is not going to be the most difficult integral you've ever seen. Integral dx here from a to c. So it's just a of t times xc minus xa. So this tells us another interesting lesson about how to think about the Friedmann-Roberts and Walker metric. It says that the actual distance between these two galaxies is given by the difference in their x coordinates times this function a. But it depends on time. So actually, right now, so at the second summer school here, these galaxies are actually farther apart than they were at the first. It's not evident the way I've drawn it. So co-moving coordinates are sort of sneaky. If you work in co-moving coordinates, it appears like nothing is moving because this is at the same x-coordinate it was before, that's at the same x-coordinate it was before. But actually, to these observers who live in this space-time, they're going to feel that these galaxies are receding. They're moving apart if A is an increasing function. So if A is increasing with time, then they will feel that they're in an expanding universe. Any questions about that? Yeah.
So, the GR thinking about the related to the coordinates.
Yeah.
You just think about picking a particular break or the place that corresponds.
Yes.
So in this case of the FRW metric, it's T and this S.
Yeah.
Like what physical break do I think about?
Good question. So the way I like, first of all, you're allowed to pick any coordinate system you want. But this is the simplest one, I feel, for what we're going to talk about today. I like to think about this as the frame of these co-moving observers. So if you have this network of all these different observers who are all on their own co-moving galaxies, what's nice about that is then the time in the metric, the t-coordinate is just the time they measure on their clocks. And what's also nice is that the x, y, and z coordinates of these galaxies are just constants in that frame. The one subtle thing is that these observers will feel that they're all moving away from each other if A is increasing with time. So think of the Friedmann. So think about if you take a snapshot, for example, of an expanding universe at a given time t, and you say, okay, this is what I'm going to now actually interpret x as the actual distances in meters at that time. What this is now saying is that at any later time, all the relative distances are the same, but all the distances have been scaled by the same factor. It's like you change the labeling on your meter stick from meters to feet or centimeters or whatever. Okay? And I'm glad you asked this question because it leads exactly to the next thing I wanted to say here, which is, so if we just write out more explicitly, right, the distance between co-moving objects d, like between these guys, right? It's equal to whatever the distance was at some initial time. Let's say that this is time t0, okay? Let's say that the distance at this time is d0. time, a at the other time divided by whatever a was at t0. Or, since we work hard to be lazy in cosmology and want to write as little as possible, we'll define a0 to just be whatever the function a was at this reference time. Usually what we do in cosmology is we pick this t0 to be today, or the day you were born, or next year, which is all the same time in the cosmic perspective. Okay? And that now we can say something about the velocities that these guys are going to observe. The velocity that people in the Tesi summer school are going to attribute to the Schmesi summer school is just the derivative of this d, right, with respect to time. So we take the derivative of this. We have d0 a dot over a0. And now, just for fun, let's look at the ratio of the velocity with which these guys see this recede to the distance to that galaxy. Okay? So let's plug in the velocity we had. We had d0 a dot over a0. And then we divide that by the distance, which we just agreed is d0 times a over a0. And we see this d naught cancels out. The a naught also cancels out. And we're left with just a dot over a. And this is a quantity which is so important in cosmology. We give it its own letter. We call it h. So h is, we call it the Hubble parameter. People used to call it the Hubble constant, but that's a really stupid thing to call it because it's not a constant, of course. It depends on time. Edmund Hubble was very modest when he introduced it. He called it K in his famous paper. I think he picked the letter near H in the alphabet because he was hoping someone would call it H later on. So the Hubble parameter H is just defined as to be a dot over a. If you look at this thing, it has units of inverse time. Right? So H inverse has units of time. H inverse is roughly the age of our universe, as we're going to see. And what this says here, we just derived, is that the velocity between any two objects that are both co-moving is just equal to the distance between them. Wait, I think, did I lose? Yeah, I lost a distance somewhere. Where did it go? Where did it fall off? I had V, I had a D naught, ta-da. Oh, no, oh, sorry, yes, of course. Here we have it, V over D, exactly. V equals HD. This is usually known as Hubble's law. So it says that whatever galaxy you're on, whatever co-moving object you're on, you're going to see everything else moving away from you. How fast does it move away? Well, the speed is, this is a vector, you can easily generalize this to vectors. The recession velocity is simply equal to the Hubble parameter times the distance vector away from you. So you see something over there receding in that direction, something over there receding in that direction. If it's 10 times as far away, you see it moving away 10 times as fast. Okay? When we say that our universe is expanding, we mean simply that H is positive. Yeah? Absolutely. So I'll talk a lot more about that, but basically, measuring distances is one of the trickiest things in cosmology. The easiest way to get started is to measure distances to nearby things like other stars. If you just for a moment hold out your thumb like this and all in front of you, just try it. And then blink alternately with the left eye and the right eye. Do you see your thumb jumping left to right? Try it. Don't be shy. I'm not going to misinterpret this as you flirting with me. Do you see it jumping left to right? Okay, now try it with your thumb half as close. Or half as far. Do you see it jumping by a bigger angle? It's not easy to see, not hard to see that in the small angle limit, the jump angle is just inversely proportional to the distance. We have a fancy name in astronomy for the jump angle. We call it the parallax. And the farther away your eyes are from each other, the bigger the angle is going to be and the more easy it is to measure. You can measure the distances to things nearby by this. That's in fact how your stereo vision works, of course. That's what your brain has a module doing exactly this. But Earth itself is orbiting around the sun. So if you take a photo of the sky with a telescope right now at the summer solstice, and then 6 months later, Earth has moved over by 3 times 10 to the 11 meters. And you compare those photos, you see a lot of stars have jumped from left to right like this, by now big enough to measure. So then by just direct trigonometry, you get the distance. Then there's all sorts of more difficult techniques for going farther than that, which we can talk about depending on how much time we have. But the bottom line is there are nice ways from using signals. You say you need to have some sort of signal, and that's exactly right. The signal is almost always light for doing it. But fortunately, by measuring light signals from the distant universe, we can measure these distances reasonably well. Okay? So let's do a little more now with the Friedmann-Robertson-Walker metric to get a bit more intuition for it. So far, I've just talked about... oh, there, yeah, thank you. Perfect, that's enough. Yeah, great. So far I've just talked about this as a free function, a of t, but obviously it has to obey some kind of equation, which we should solve to figure out what it is. I want to just also tell you about one more very important quantity first, which is the redshift. Okay. If we look at distant objects, if space has expanded by a factor of 2, for example, since the light was given off, the light waves from it also stretch by a factor of 2, like you might expect, as space stretches. So they come here twice as long. If they were blue, they'll now be, they shift towards the red side of the optical spectrum. We call it redshift. And we define the redshift in cosmology so that the redshift z is such that 1 plus the redshift equals the size of our universe now divided by the size our universe had before. So the redshift z is just defined as a naught over a minus 1. 1 plus the redshift is just how much light has been lengthened by, or the factor by which our universe has expanded. Okay? It's challenging to measure the distances. It's super hard, but it's very easy to measure the redshift of things, because you just measure the spectrum of some hydrogen line or whatever, and you're like, oh, it's 10% too long. So actually, we astronomers get kind of lazy and tend to use the redshift as our time variable. It's sort of a strange concept. But you'll hear astronomers say that, oh, this happened at redshift 5. And that was even in one of your questions. You asked about at redshift 20. What do we mean by that? We just mean, if we say something happened at redshift 10, we mean it happened at the time such that light given off then has been redshifted by a factor 10 by the time it gets here today. It's a little bit confusing because this is the time variable that runs backwards, right? Big Z, big redshift means long ago, small times. Pop quiz. What's the redshift right now? What the redshift corresponds to today? 0. Very good. Awesome. So now let's solve for a of t. How do we do that? Well, we take the Einstein field equations of general relativity. We plug in the Friedmann-Robertson-Walker metric. If we're lazy, we do it with Mathematica. Well, it's not too hard to do it by hand. And then you find that actually this is only a solution to the Friedmann-Robertson-Walker metric if the following equation holds, which is known as the Friedmann equation. It was first discovered by Alexander Friedmann in the early 1920s, was completely ignored by pretty much everybody. And he sadly died also before he really got much recognition. But I think this was one of the most important equations ever derived. It governs how our universe expands. He was the first person to really realize that our universe could be expanding. It says that A dot divided by A, which when you square it, so A dot over A, haven't we seen that before? It's just the Hubble parameter, right? So that's just h squared. It must equal, in order to solve the Einstein field equations, 8 pi times Newton's constant over 3 times the density of stuff in space. Adding up all sources of density, ordinary matter, dark matter, light, whatever, minus this k. There's going to be a k somewhere in the equation because there's a k in the Friedmann equation, right? Times the speed of light over a squared. Okay, this is the Friedmann equation. This is different. It's a first order differential equation, and you can solve that for this function a, if you know how this density evolves with time. Because this is also this density we agreed doesn't depend on position, because we said we were going to study homogeneous, position-independent solutions, but it does depend on time, right? I'm going to write this also in an even simpler way, because I like to pick the notation that makes my equations as short as possible. So I define the total density as including density of all the ordinary stuff, and then this term also, I absorb it in there. I define a curvature density. This term here has to do with space being curved, right? Because if k was 0, we said space is flat. If it's plus 1 or minus 1, there's curvature in space, and that will affect also the rate in which it expands. One other little handy math fact: the Hubble parameter, which we defined here, you can also see that this is just the time derivative of log of the scale factor. Right? Okay, so what's this? How do we solve this? We get a different solution depending on how the density is going to behave. So what kind of stuff do we have that contributes to the density of our universe? Let's do it. Let's call out. What kind of stuff do we have in here? Give me some examples. Matter. Good. Matter. If you're writing this down in your notes, keep a mystery slot here, here, and here also, because there will be things coming there, and I want to have them in this order. Matter. For matter, if I have 1 kilogram of matter in this volume, and now our universe expands into a bigger volume, into twice into something with into a sphere, say, of twice the diameter. What happens to the density? What factor will it change by? It'll drop by 8. Exactly, because the density of matter goes like 8 to the power minus 3. Because the total amount of kilograms, the mass is conserved. Right? So it has the density is mass per volume, it has to go like inverse volume. What other kind of stuff do we have? Is there any kind of stuff that doesn't behave like that? Radiation. Good. If you take the number of photons in a cubic meter, the number density of photons per cubic meter, of course, goes like 8 to the minus 3, because the number of photons is conserved when you expand space. But in addition, we talked about how the wavelength of each photon also doubles. And how does the energy depend on wavelength? Well, the wave energy goes like the frequency. It's hf, right? So if you double the wavelength, you have the frequency. So that gives another factor, a, in the denominator. So now we get 8 to the minus 4. Radiation dilutes faster than matter. What else do we have? Any other kind of weird stuff? Dark energy. Yes. And as far as we can tell, it doesn't dilute at all. Extremely weird. So a to the 0. It's just constant. Finally, I decided to define curvature density, just so we could unify this a little bit. Look at this term. How does it depend on a? 8 to the minus 2, because k is just plus 1, minus 1, or 0. Okay? So now let's do some solving. Let's save a little space here so we can write the answers. And For example, suppose we have the matter-dominated case. If you go back to redshift of 10 or redshift of 100, when dark energy was not so relevant, you see, eventually, dark energy will always win because it dilutes the least. And dark energy has already started dominating now, right? At very early times, radiation seems to win. But there was a long period when matter dominated. So then we have rho goes like 8 to the minus 3. Let's just solve this Friedmann equation and see what happens. So dA dt, that's A dot, right, divided by A. This is the Hubble constant, right? According to the Friedmann equation, that's supposed to equal this, but it's squared here. So we take the square root of the right-hand side. Matter dominated means there's no curvature. We ignore this thing. This goes like 8 to the minus 3, where we take the square root of it. So I'm going to write proportional to square root of A to the minus 3. In other words, A to the minus 3 halves. Okay. So what can we do here? What is this? It's an ordinary differential equation. It's separable, meaning we can separate all the A stuff on the left side and all the T stuff on the right side. On the left side, we have our dA. What else do we have with an A in it? We're going to bring this A to the minus 3 halves over, so we get A to the plus 3 halves divided by A. So we have A to the 1 half. And that's supposed to be proportional to dt. Now this is screaming, this is whispering something to me. Let me see if I can hear what it's saying. Integrate me. Integrate me. Did anyone hear what did it say? Integrate me. Okay, let's do it. So what happens then? We're going to get A to the, what's the integral of this? A to the 3 halves is proportional to t plus some constant. Now, this constant is just the overall offset of time, clearly. So we can define t equals 0 to be whatever we want. If it's very convenient to define it, the constant to be 0, because then t equals 0 is going to correspond to A equals 0, which is sort of a big bang, right? So let's do that. And this tells us now that A is proportional to t to the 2/3. Famous solution. So we're going to write that in here. This matter-dominated case says that the universe expands as t to the 2/3. Yes? How what? Oh, because I decided before we talk about the full general solution, when we have all the kind of stuff to do our actual universe, I want to pick at this and look at some special cases. So I said, imagine, I'm glad you clarified, let's look at a fictitious universe which has only matter. It has no curvature. Space is flat, and it has no radiation in it, and it has no dark energy in it either. Then what happens? That's the question I ask now. Okay? No, we don't actually. I'm very glad you asked this. We learned sort of in kindergarten that matter curves space, and so if there's matter, there's got to be space, and if there's matter, there's got to be curvature. But actually, what this shows is that the truth is a bit more subtle. It's really space-time which is curved by matter, not space itself. And if space is expanding, then the time behavior of this metric can actually absorb all the curvature in principle which is linked to the matter, so that the space itself isn't curved. So let me address this more specifically. What general relativity says is that whenever you have matter or energy, space-time is curved. It's a 4-dimensional kind of curvature. So you're completely right about that. But this curvature corresponds to 3-dimensional curvature of a spatial slice. You pick a fixed t-coordinate and ask, is space itself curved? And what the Friedmann, what the Friedmann, Roberts, and Walker metric says is actually there are 3 cases. You can get a solution with stuff where space is perfectly flat, or a case where space actually is curved back on itself like the surface of an orange, or a hyperbolically curved space like a Pringles potato chip or a horse saddle. And in particular, if you don't want curvature, then you set this to 0, there's always a magic expansion rate h, such that you will get no curvature at all. Or turning it around, if you know how fast our universe is expanding, if you know the Hubble parameter, there's always a certain magic density that if you have just that right density, space will be flat. Higher density, it curves back on itself. Lower, you get the opposite kind of curvature, okay? So we're now looking at the simplest solution where space actually has no curvature, which actually turns out to be this. We have measured the curvature to better than 1% accuracy now with the Planck satellite, and it's totally flat. Yet there's clearly stuff around. Yeah? That's what? Yes. But as we're going to see, in fact, as far as we can tell, it has always been this way, at least since 10 to the minus 34 seconds since the beginning. We've gone through different phases, as I'll talk more about next time, where we're dominated by different things. And it turns out there was a long epoch from redshift of 1,000 or thereabouts until a redshift of a few, 3 or so, when we basically had this solution. It's a very good approximation. Okay? So let's just very quickly look at the other cases. Suppose we have radiation. We can do the exact same kind of math here. I'm not going to bore you by doing it on the board. So you can easily check that yourself. Then you get simply a different power, θ 1/2. Again, our universe expands, but it's a different power. Let me say also that if you want to, there are a lot of resources online and a lot of books where you can read about the foundations of cosmology. I'll tell you what my favorite is. My favorite place to go is the most recent book by Steven Weinberg on cosmology. I'm not talking about his gravitation book or his field theory books. He wrote a cosmology book. It just came out. Beautiful book. And you'll find all of this stuff done very, very nicely there. So that will be my number one go-to resource if you want to go through this sort of at book level of detail. And Steven Weinberg, I just feel he has such a clear pedagogical thinking style. There's nothing vague or fuzzy about what he does, and it's all there. And no, he did not pay me to say this. Even though he did once tell me, when I admitted that I hadn't finished reading his quantum field theory books, that the important thing about his books is not to read them, but to buy them. We started about 5 minutes late. Can I go to 5 minutes past? Sweet. What about curvature? This case corresponds to t to the first power. Now, if you have something moving along, that means a dot, the speed, is kind of constant. It's like coasting along, no acceleration or deceleration. Here we have a deceleration, because the derivative of this gives a speed which gradually drops. That's kind of natural, because gravity tries to pull things back together. So this case, pure curvature, that's the case where you set rho equals 0. There's no matter. So sure enough, there's no gravity, no deceleration. It's just the coasting along universe. And you might say, this is kind of weird. How can you have a universe with no stuff in it that still has this, is expanding? Sure enough, you can change coordinates in that case. So you get Minkowski space. Finally, dark energy. Here you get a slightly different solution. So let's look at that together on the board also. Now, I said that we can also write h as just the time derivative of log a, right? So time derivative of log a. That's supposed to equal the square root, again, of the metric, of the density, rather. But if the square root of, if this is constant, we look at now a dark energy dominated universe, which is what we will become in the distant future. No curvature, the matter and the radiation dilute away, it's 100% dark energy. That means this whole thing is just constant. That means h is constant. H no longer, the Hubble parameter stops depending on time, right? So we get this equation. So that's not very hard to integrate. That just says that log A equals ht plus constant, which is just saying that A itself goes like e to the h times t. Let me write that down here. Now we get exponential expansion, which is kind of crazy, but that's exactly what's beginning to happen now. Our universe is expanding gradually faster and faster. We're asymptoting to expanding exponentially. Okay? Let me just take a few minutes just to summarize, since I'm very grateful to you all suffering through this much math here, even in our first lecture. So let's just take a few minutes to summarize what have we learned from this math? What was the point? What's the big picture here, okay? So let's just get a bit more light on the subject. You can see this, okay? This is brief history of our universe, like we talked about initially. And here I've written out in yellow some of these different solutions we studied. So right now we're getting more and more dominated by dark energy. Our universe is beginning to expand exponentially, as I've tried to indicate on this picture here. The size from here to here is supposed to indicate the scale factor, but it's of course not the scale at all, because we've expanded by a much bigger factor than 2 since back here. But we're getting vacuum dominated. For a long time here, we were matter dominated. So the universe expanded like t to the 2/3. Here, now radiation, if we head back and dilutes like a to the -4, right, rather than a to the -3. So as we go back, eventually radiation becomes more dense than matter. And there's an epoch at redshift 3000 or so when radiation density now equals matter density. We call that matter-radiation equality. So during this period here, it's the radiation-dominated solution. Our universe is expanding like t to the 1/2. And then very early on, I mean, the most popular theory for what happened is inflation, which says that once again we were dominated by some kind of weird dark energy and had an exponential expansion. It went on and kept doubling the size of our universe every 10 to the -34 seconds or so. But then this weird substance, that dark energy, decayed away somehow, and inflation ended, and the energy from all that got dumped into hot plasma, and we went through a radiation-dominated phase. So to get the actual history of our universe, we need to have a model for how the density consists of many components. So we can write down rho as a function of A, and then we can solve and get the whole thing, okay? Let me also just say a couple more words about how I like to think about, in summary, everything we know about the history of our universe. So imagine we're standing here on the right side, where I drew this eyeball, and we're looking back like this, okay? What do we see? Well, it actually reminds me quite a bit of a sort of strange dream of giving Teiji lectures, where it's a little bit of an alternate reality. So imagine for a moment me looking out into our universe, okay? And I'm looking out into this classroom here. Each one of you is a galaxy. So I look out here and I see those of you students sitting in how old are you, Nicholas? But in this dream, actually, you are 85. In fact, everybody in the first row is in their 80s and 90s. I'm like, that's kind of a coincidence. Because the people behind you there are like in their 60s, and then there are a bunch of people in their 50s and 40s, and then there is a bunch of high school kids. Who invited them? You know, it must be really precocious. And then some toddlers and some babies sitting in the back. And then the last row is empty. And then beyond that empty row, I see that the far wall of the classroom is glowing with a strange glow of microwaves. Like, what on earth? This is a really weird dream. What's going on? But this is exactly what it looks like when we look out with telescopes in our actual universe. Because as we discussed, right, the farther out I look, the farther into the past I'm looking. And I'm seeing galaxies, therefore, that are much younger, because they haven't had time to get old yet. So that's exactly what we see. We see big, mature galaxies nearby and then smaller and younger galaxies, and then baby galaxies farther away. And then we see the cosmic dark ages. That's the empty back row of the room. Nobody there. At least nobody who's shining light at me. Of course, there's still stuff there. There's the hydrogen gas and the 25% of helium, which will eventually cluster into all this stuff. But you can't see it at all with regular telescopes. And we need other techniques. I'm going to tell you in the third lecture about 21 centimeter tomography, which is something I'm working very hard on with my group at MIT. They're trying to map this stuff using radio waves. And then what about the thing I said about the strange glow coming from the back of the classroom? Well, all of this hydrogen here between the galaxies, when I was a kid, I saw the black in these photos. I thought, oh, that's vacuum. But now, of course, you know better. You know this is hydrogen gas. It just looks black because it's transparent, just like the air in this room. But when you go farther and farther back, this gas gets hotter and hotter. And at this point, at a redshift of about 1100, 400,000 years after a Big Bang, it's so hot that the hydrogen becomes a plasma. And the plasma is opaque. Can't see through it. So it's just like behind all these galaxies, I see a wall. And yet, of course, a hydrogen plasma will give off radiation, which we should be able to detect. How hot is this when you do the math? It was about 3,000 Kelvin, about half as hot as the sun. So if you went back there, you would immediately fry and die. But our universe has expanded by about 1,000 since then. Space has stretched out 1,000-fold. The wavelengths of those rays got 1,000 times longer. Z equals about 1,000. So the temperature, therefore, is 1,000 times smaller. It gets here as 3 Kelvin, not 3,000 Kelvin, which means it's microwaves. That's why the back wall is glowing. And this slide here summarizes all these key ideas that we've discussed in today's class. And on that note, thank you very much, and see you tomorrow.